All right, chapter 26, problems. Pat's near point and far point are accurately measured to be 37.5 centimeters and 66.6 centimeters respectively. So we have near point equals 37.5 centimeters, far point equals 66.6 centimeters. What prescription lenses does Pat need, I hate typos, to be able to have both normal near and far vision? Assume that Pat will wear eyeglasses with the lenses 2 centimeters from the eyeball. What vision problem or problems does Pat have? She has two problems because the normal or ideal for the near point is 25 centimeters, and for the far point, it's infinity. So neither of those is correct. That means she has a problem associated with each one. So let's start with the far point. If the far point is closer than infinity, that is myopia or nearsighted. Nearsighted means you can see near things, but she can't see near things either. So she has a complication here in that she can't see far things or near things. She can't be farsighted. If you can't see near things and you're nearsighted, that means you must be presbyopic. She has presbyopia, which, as I said, means old person vision. Something I'm just starting to get. That old person vision occurs because the crystalline lens in the eyeball stiffens, so you can't accommodate as much. You can't flex it as much as normal. So she's going to need two lenses, one lens to fix each of these problems. So that means she's going to need, so we have both of them there, she's going to need bifocals. One lens to correct the presbyopia, one lens to correct the myopia. So for her near vision correction, that is for her presbyopia, we're going to have her eyeball, and I'm going to draw an optical axis here just to make life good. A principal axis, if you will. And we want to put an object at the normal near point. So that means I'm going to have this here is 25 centimeters from the eyeball. And we want it to make an image that she can focus on. So the nearest she can focus is 37.5 centimeters away. So it's going to make an image. This image should have been a little bit taller because it's a little bit farther away. That is 37.5 centimeters from her eyeball. All we have left to do is put our lens in here. So here's our lens. And this is going to be a concave type lens. You use concave type lens to correct this. And we would find that in our work here. So it's not like you have to have that memorized. Now I need to identify what is distance object and what is distance image. Notice this is distance object. So that's going to be 25 centimeters minus the 2 centimeter standoff. So it's going to be 23 centimeters is her distance object. And let's see. In this, well, I should have put 25.0 there. 25.0, so 23.0 centimeters. And then the distance image is the 37.5 centimeters minus 2 centimeters. So 35.5 centimeters. The astute student right now is saying not so fast. Not so fast because the image is on the same side as the object, which means it's a negative image distance. So now that I have that laid out, 1 over f is equal to 1 over distance object plus 1 over distance image is equal to the power of the lens. So that's going to be equal to 1 divided by 35. Oops, distance object was 23.0 centimeters. Now I'm going to change that from centimeters to meters, 0.230 meters. The reason to do that is because power is given in units of inverse meters. Plus 1 over, and the distance image is minus 0.355. And so, assuming I put that in my spreadsheet correctly, and I'm actually going to check real quickly here. I have power. Nope, I didn't put it in correctly. So my power should be 1.53. And 1.53. I am once again doubting myself here. That's 23. Yeah, okay, so well, unless I made a mistake, which at this point I do not think I did. 9, 10, yeah. I have 1 over 23, 1 over 0.23, plus 1 over 0.355 is equal to, plus 1 over minus 0.355. 1.53 diopters. Now, if it's 1.53, that's actually going to be this type of lens. Now, I'm going to have to review that. I'll probably still post this, but I was thinking that it was going to be the other type of lens. Oh, yes, yeah, no, that's fine. Now to correct for the far point. That was the near point correction. Now the far point correction. So far point correction. So for the far point correction, we once again have the eyeball here. And I'll put a principal axis on here. And we're going to have an object at the ideal or normal far point, which means that my distance object is equal to infinity. Now, once again, somebody might say, hold on, not so fast. Well, infinity plus or minus 2 centimeters is still infinity, so it doesn't matter. It's going to make an image at the actual far point. And so this distance here is 66.6 centimeters. And now we have to put our lens in. Now it's going to be our concave meniscus with our 2.00 centimeter offset, which means that distance image is equal to minus 64.6 centimeters. Minus 64.6 because that 2 centimeter offset. Distance object is infinity, so using the thin lens equation is actually pretty trivial. 1 over focal length is equal to 1 over distance object plus 1 over distance image equals 1 over infinity plus 1 over minus 0.646 meters equals, let's just make sure I did that, yep, equals minus 1.55 diopters. So she has a 1.53 to correct the near vision and a minus 1.55 diopters to correct the far vision. All right, so that's our vision. Make sure you understand what hyperopia is. Hyperopia, also known as farsightedness. You can see far just fine, but you have a problem with your near point. You might look back at what I just said and did and say, wait, but you just said that's presbyopia. You cannot have hyperopia and myopia at the same time, because those are fundamentally a problem with either the curvature of the cornea or the length of the eyeball. So myopia, the eyeball is too long, or the cornea is too curved. So you can have laser vision correction by flattening that cornea. Hyperopia, either the eyeball is too short or the cornea is too flat. So the correction is a little tougher because you need to make the cornea more curved. And how do you ablate or vaporize material to make it more curved? Well, you have to make it thinner at the edges, and that's why it's a little trickier. So hyperopia and myopia are opposites. You cannot have both. Presbyopia is a hardening of the crystalline lens, and that can come with either. If you have presbyopia and hyperopia, you don't really notice that you have two vision problems, except for, your far point starts getting, actually, no, you just really don't notice you have two vision problems. If you have presbyopia and myopia like this, you can't see near, you can't see far, you're not enjoying it, and you need those bifocals. All right, going on to the next problem. You're given two lenses with focal lengths of 93.5 centimeters and 3.65 centimeters. What kind of optical instrument will these lenses be useful for? Now, the two optical lenses that we've looked at were telescope and microscope. The purpose of the telescope was to magnify distant objects. The purpose of the microscope was to magnify small objects. They have fundamentally different purposes. I used to think when I was a child that a microscope and a telescope were just the opposite of each other. You turn it around and it changes from one to the other. Not so. They're optimized for different types of jobs. So a microscope is made with two short focal length lenses. With the shorter being the objective. The telescope, on the other hand, is made with a long and a short focal length lens. Longer F is objective. So you look at these and you ask yourself, okay, are those both short, or is one short and one long? I would say 93.5 centimeters is long. So that means this is useful for a telescope. So what's the magnification for a telescope? The magnification is minus focal length of the objective over focal length of the eyepiece. So it's just a direct substitution. That's going to be minus the long one, 93.5 centimeters, over the short one, 3.65 centimeters. And that gives us a magnification of minus 25.6 times. The minus sign means it's going to be inverted. And then the length is equal to the sum of the focal lengths. So that's 97.2 centimeters is the length. So that was kind of a short problem, really. But you had to do your analysis there and determining, hey, which type of instrument fits these lenses? Now you're going to have one problem of the nature like one of these two on the test. So hopefully you can understand how we did both of these.